welcome in this session. In this session, we are going to continue in the derivation of numerical differentiation formulas for evaluating derivatives of functions. So in the last session, we derived the Newton forward formula for finding the first derivative of a function. So in this session, we are going to derive the formula for finding the second derivative of a function using Newton forward interpolation formula. So higher order derivatives. So the interest is to calculate the second derivative of the function using Newton forward difference formula approach. Now, remember from what we did last, recall that the first derivative of the function f of x, we found the answer to be 1 over h into first forward of f naught plus 2p minus 1 over 2 second forward f naught plus 3p squared minus 6p plus 2 over 6. This is third forward plus 4p power 3 minus 18p squared plus 22p minus 6 over 24 fourth forward of f naught plus 5p power 4 minus 40p cubed plus 105p squared minus 100p plus 24 divided by 120 fifth forward of f naught plus 6p power 5 minus 775p power 4 plus 340p cubed minus 675p squared plus 548p minus 120 divided by 720, and this is multiplied by the sixth forward of f naught plus other several terms. I remember this, we call it equation 3 in the previous derivation, the previous class. So we know that from calculus, f double prime of x is the same as d squared dx squared of f, which is the same as d dx of df dx. So this is the interpretation. But you saw, but df dx is the same as 1 over h from what you have done in the previous class, dp. So it means that where there's df dx here, I can replace by 1 over h df dp. So I'll have d dx of 1 over h df dp. 1 over h being a constant can be taken outside the derivative differential operators. So 1 over h d dx into d dp of the function f. Now this and these are differential operators, so we can always commute them. So 1 over h d dp, and then d dx of f. But you see, this is 1 over h d dp, and d dx of f is the same as 1 over h df dp. So this can be written as 1 over h df dp. So still you factor out this 1 over h, and so it'd be 1 over h times 1 over h is 1 over h squared, and then d dp of d dp f. So which tells us that the answer would be d squared f dx squared is 1 over h squared d squared f dp squared. So which simply means that then if we are able to differentiate the first formula, and then we the first formula, and then we multiply by this scalar, then we'll have the answer for second derivative. So therefore, our second derivative of the function is the same as 1 over h squared d dp of d dp of the function f, which is the same thing as 1 over h squared d squared f d squared dp squared of f. Yes, second derivative. So we are the same as 1 over h squared, and then we differentiate the first derivative with respect to p, because actually this means you get the second derivative by differentiating the first derivative. So differentiating this formula 3 here. So the first term will be 0 because there's no p. So this will give us 2 over 2. Because the derivative of -1 is just 0. So it'll be 2 over 2 second forward of f naught. Here we'll have 6p minus 6 over 6 third forward of f naught, etc. So the first one will be 2 over 2 second forward of f naught. When you go to the next term, you'll get the answer to be 6p minus 6 over 6 third forward of f naught. Next term, when you differentiate, you'll get 12p power 2 minus 36p plus 22 divided by 24 fourth forward of f naught, plus next term, you have 20p power 3 minus 120p power 2 plus 210p minus 100 divided by 120 fifth forward of f naught plus our next one will have 30p power 4 minus 300p power 3 plus 1020p power 2 minus 1350p plus 548 divided by 720 is the sixth forward of f naught plus other several terms. So remember, what is giving me this answer is just simply differentiating each term of equation 3 with respect to p, and then this is what we get after simplification. Call this one formula 5. So formula 5, just as we saw in the other case, formula 5 is used to compute second derivative of the function with respect to x at or for non-tabulated values of x. That means that you'll be asked to find the second derivative at a value of x which is not among the values given in the table for non-tabulated values of x. Similarly, as we saw in the other case, if we set x to x-naught, then from x equals to x-naught plus ph, we have x-naught equals to x-naught plus ph. So which means 0 equals to ph, which means p equals to 0. So replacing p equals to 0 in formula 5, we get, so we'll have the second derivative at x-naught, which is same as df dx at x equals to x-naught will be now 1 over h squared. Now when you put, so this would be, remember this would be 2 over 2 just 1. So just have second forward of f-naught. And then this other term, you put here 1. You put where there's p, you put 0. So 0 times 6 is 0. So minus 6 over 6 is minus 1. So we'll have minus third forward of f-naught. And then you put 0 here, put 0 here. We'll have 22 over 24, which is just 11 over 12. So plus 11 over 12. And then fourth forward of f-naught. And then in the next term, if you put 0 here, you put 0 here, you put 0 here, so we'll have minus 100 divided by 120. And then, so minus 100 divided 120 gives you minus 5 over 6. Minus 5 over 6. Fifth forward of f-naught. And then plus several other terms. So I'll call this one formula 6. So formula 6 is used to compute second derivative at tabulated value, i.e. x equals to x-naught. So that is how we get the second derivative using the Newton forward interpolation formula. But we can also get the third derivative by simply now coming and multiplying 1 over h power 3. Differentiate this formula here with respect to p, you'll also be able to get the expression for third derivative. And similarly, you can derive the formula for fourth derivative by multiplying 1 over h power 4 times the derivative with respect to p of the function you'll get after getting the third derivative. And the process can continue to get even other higher order derivatives. Thank you.